The focus of this video will be what's known as the limit laws, but we'll begin with something simpler. Let's begin with the limit of the constant k as x approaches a. That limit will always equal the constant k. How does it work? Well, let's take a look at a value of k where it equals 4. If we were to graph it, it would be a horizontal line whose heights would always be equal to 4. So it really doesn't matter what we define our a to be, the left-hand limit and the right-hand limit will still be always at the same height of 4. So in our example, limit of 4 as x approaches 3, that's going to equal 4. Alright, let's move on to another one, in which the limit of x as x approaches a will always equal a. How does that work? Well, x can be represented with the identity function. That's where the x and y coordinates will always be the same. So if we're going to go limit of x as x approaches 3, we're going to keep getting closer and closer to the coordinate 3, 3 from the left and from the right, and we can say that the limit equals 3. Now, these limits are simple limits, and they're straightforward. If we're going to do mathematical proofs or more complicated limits, we require the precise definition of a limit. That's not going to be part of this video. So let's just move on. When you're working with limit laws, you must have the following givens in place. You must have the limit of f of x as x approaches a, and the limit of g of x as x approaches a exist. So if we have that, we can actually then go ahead and say the limit of the sum of f of x plus g of x as x approaches a equals the sum of each of the individual limits. Or, more specifically, the limit of f of x as x approaches a added to the limit of g of x as x approaches a. And if you can do this with sums, you can also do this with differences. Now let's see how these limit laws can be applied. Well, we have a limit of a quantity x plus 4 as x approaches 3. I'm going to look at the x as the f of x in our limit law, and I'm going to look at the 4 as the g of x. Now, I can break up these two limits into two individual pieces and add them together, as long as they exist. Well, the limit of x as x approaches 3 we discussed in the last slide. That works out to be 3. Just like we also discussed, the limit of the constant 4 as x approaches 3 equals 4. So now that I have 3 and 4 and they both exist, we're allowed to add those together and come up with a sum of 7. But here's the key thing. As I said at the beginning, if the limits exist, we can apply the laws. If either limit does not exist, then the limit laws cannot be applied to our problems. Before we continue on with the limit laws, from this point forward, unless I tell you differently, assume that the limit is where x is approaching a. Why? Who wants to keep hearing that over and over again? And let's save my voice for a minute, okay? Let's begin with a new limit law, in which we have a limit where a constant k is multiplied to f of x. With that constant k, you're actually allowed to pull that out of the limit and say k multiplied to the limit of f of x. Speaking of multiplication, the next limit law has f of x being multiplied by g of x. If you want to find the limit of that quantity or of that product, feel free to take the limit of f of x and then simply multiply it to the limit of g of x. And if you can do it for multiplication, you can do it for division as well. The limit of f of x over g of x will equal the limit of f of x being divided by the limit of g of x. But remember, you can't divide by 0, so we have to make sure that the limit of g of x does not equal 0. And if it doesn't, feel free and go ahead and apply this limit. So here's the practice problem. The limit of the quantity x squared plus 4x as x approaches 3. Well, I realize that x squared plus 4x can be factored. The greatest common factor that can be pulled out is x. So I could rewrite it first as the limit of x times the quantity x plus 4 as x goes to 3. Now, the second bullet point can apply. I can say the limit of x as x approaches 3 is then multiplied to the limit of the quantity x plus 4 as x approaches 3. Going all the way back to my first slide, that first limit, the limit of our f of x, is going to equal 3, while the limit of our quantity x plus 4 was established to be 7 in the last one, and that's why 3 times 7 is 21. Our next limit laws requires us to have another element to the given, this being n is an integer. And with that, we can now evaluate the limit of f of x being raised to the n, as that will equal the limit of f of x being computed first, and taking that value and raising it to the n. And since we are dealing with exponents, we will also be able to work with nth roots. In this case, the limit of the nth root of f of x will equal the nth root of the limit of f of x. Remember, nth roots can be rewritten as exponents of 1 over n. And since we are dealing with nth roots, that little last part where it says if n is even, you can only take even roots, square roots, fourth roots, sixth roots of non-negative numbers. Odd roots you can take for all reals, and that's what that says. So what's our example problem? Well, it should look familiar as it's the same problem we did before. The limit of the quantity x squared plus 4x as x approaches 3. But this time I'm going to do something different. I'm going to break it up as an addition problem. And then I now have the first rule I can look at, the limit of x squared being our top bullet point, which I can do the limit of x as x approaches 3, and then take that value and square it. And that will be 3 times 3. Now our second one, I have that constant 4x, and I can pull that 4 out, and now I can go 4 times the limit of x, or 4 times 3, and that still gives us a result of 21. The last two limit laws that I'm going to introduce here will be a merging of the limit laws from the last slide. That would be the exponent and nth root. And if we actually take those and merge them from the very first slide, we can say the limit of x raised to the p over q as x approaches a will equal a raised to the p over q. We can also say the limit of a function f of x raised to the p over q will equal the limit of f of x computed first, which is then raised to the p over q. And for our sample problem, we're going to do the limit of the quantity x plus 5, take that value, raise it to the 2/3, and find that as x approaches 3. So what we'll do is we'll actually find that limit first of the quantity x plus 5. And when we do our addition rules and our rules from the beginning, we come up with a value of 8. That value of 8 then can be raised to 2/3. Now what I'm going to do is I'm going to actually break that up as a power to a power. And that power would be 8 to the 1/3 raised to the second. But 8 to the 1/3 is the cube root of 8. So I'll do the cube root of 8 first, which works out to be 2. I'll take that 2 and square it, and I'll come up with 4.